Okay, so in this video and the next, we will talk about using gradient descent for solving these sort of more complex image recognition problems first to essentially optimize the loss function. And then we will find that uh, superficially it's not fast enough, and then we will improve upon it by using something called stochastic gradient descent. Okay, so let's try that. So this program is essentially gradient descent, but now applied on the MNIST data set, trying to do logistic regression. We are trying to minimize the logistic loss function. And previously, we used fmin-unc so far for all your optimization calculations. Here, we're just going to use the gradient descent algorithm where we have this function, we find the gradient, and then take a step along the negative of the gradient, and then repeat that over and over again. So let me just run through that. Run. These are all standard sections here. We're just finding out whether it's a 5 or not, our original problem that we did. Um, we are going to do 1,000 steps of gradient descent. We have a learning rate alpha, really small. We're going to evaluate, in this case, the um, gradient using a finite difference approximation, for which we need to know what the epsilon is, the accuracy of the function. For that, we are going to use 10 to the minus 12 because it's somewhat of a complicated function. And that's basically it. And then we say we are going to stop the gradient descent if the gradient has a norm less than 10 to the minus 4 or something like that. And this part is just gradient descent. We are setting up the initial seed, which is just a list of zeros. We're computing the initial value of the function. We can probably comment this out. Um, Let me comment this out. And that's about it. So let's just run through that. Um, this is the gradient descent loop. We've just plotted the very first function value at the initial seed. This is a gradient descent loop. It computes a gradient using central difference formula and then takes the next step equals current step plus alpha times negative of gradient, and then evaluates the function value at the new state, and then plots it, and then keeps doing that for 1,000 steps, or if the gradient is less than some threshold. That's it. We can use fmin-unc to optimize. Let me just comment that out. You can also use fmin search, which is another method to optimize it. Take a look at that. So let me just run through that. I guess this is the cell that we wanted to learn. So it looks like it takes about a second per step, right? So the function value is decreasing. Function value was 0.7, jumped to 0.3, and then now keeps decreasing, which is nice. So as usual, it may be that my computer is slow because I'm making this video. So you shouldn't completely trust the timing information for some of these things. In any case, gradient descent proceeds in that manner, and pretty straightforward. As long as you can evaluate the function, you can compute the gradient using a finite difference formula, and you just keep stepping along the negative of the gradient. So let me just control C out of the simulation of this optimization because it's making progress and it will eventually converge or stop making progress, and I guess we'll halt things there. Okay, so let me just close this. and just control C it out of the simulation. Okay, so that's gradient descent. So now you can implement an optimization algorithm from scratch, right? So previously we used fmin-nunc, which is a pretty sophisticated optimization method that we essentially called. Now we just implemented gradient descent essentially from scratch. Okay, so um, notice that, well, like I said, the timing information is not super reliable, but in gradient descent, what we are doing in some sense. So imagine, let me actually, I just opened the gradient descent version of the algorithm again. Here, I'm just using 1,000 data points, 1,000 images, okay? So in your fmin-nunc execution, um, we used 4,000 images for this problem. The reason why we used only 4,000 images as opposed to all the 60,000 images present was because each function evaluation, each evaluation of your logistic class function requires essentially looping through all the um, images, right? Even if it's not a loop, I guess it essentially is computing this X matrix will be a huge matrix. If it has 60,000 images, it'll have 60,000 rows. Whereas if it has only 1,000 images, it'll have 1,000 rows, right? So having 60,000 rows is very different from having just 1,000 rows or 4,000 rows. Um, and having 60,000 rows will make the evaluation of the function much slower. And that's why we're using only about 1,000, right? So what if we use 60,000? Um, then even one iteration, one evaluation of the gradient will take a much, much longer time. So if I run that, it's on step number 1, and we'll have to wait a while for it to go to step number 2. It's not even gotten to the gradient descent yet because it's just essentially sort of parsing or processing these 60,000 images through the logistic class function implicitly. Just constructing that big matrix might take some time. Okay, 60,000 by 785. I actually want to control C out. I just control C out. Looks like it's computed it, computed the function value. In any case, it's very slow if you want to process all the 60,000 variables, okay? So that's why we used 1,000 variables or 1,000 images or 4,000 images. But what's the downside of just using 1,000 images? Well, you're just using 1,000 images. You're not using the whole data set. So intrinsically, it's bad, right? So if you're using only 1,000 images or 4,000 images instead of 60,000 images, you're certainly not using all the data. Ideally, we would like to use all the data, but we see that using all the data slows the process down immensely. Okay, so that's gradient descent. That would also be fmin-nunc. Whatever method you use um, while evaluating the loss function as described so far, you will essentially incur a huge computational cost if you process all the images while evaluating this function. Okay. So the alternative is this method called stochastic gradient descent. Okay. Um, I will sort of first describe the algorithm. Well, I'll just walk us through it and then explain the word stochastic in a minute. The word stochastic just means random, and I will describe first the algorithm and then why the word stochastic plays a role in this algorithm, or why it's called stochastic gradient. Okay. The basic idea is basically to use fewer images per iteration, right? Fewer data points per iteration. Um, but do that in a manner that you do end up using essentially all the data. So can you achieve both? Sort of decrease the computational cost of each iteration, but then use all the data as the algorithm proceeds. So that's the idea. Um, so This is the same. We are loading mnist. This is all standard processing. Here, we notice that we are not pulling out just the first 1,000 or first 4,000. We are leaving in all the 60,000 or all the 10,000 images here. We're not reducing the size of the data set. So again, this is called stochastic gradient descent. Okay, stochastic gradient descent. I've written a description here, but we'll just walk through it first. So this is all set up, X matrix, number of unknowns, initial seed, which is just a bunch of zeros. And then we are going to do a 500 stochastic gradient descent steps. Learning rate is something. These are all exactly the same. We're going to use, again, finite difference approximations, specifically central difference for computing the derivative or the gradient. And for that, we use an epsilon or function accuracy of 10 to the minus 12. We will stop the gradient descent if we get to a gradient threshold of 10 to the minus 4. In other words, when the gradient is small enough. And then we have this variable called mini batch size. Okay, mini batch size. What is that? Okay, so remember we are supposedly using all the images here. Mini batch size says we're going to really use 256 images or 256 data points at any point in time. Okay, for any particular iteration, we're just going to use 256 images. Okay, so how does that work? So just remember, we're going to use 256 images at a time, but then eventually we will have used all the images. Okay, so that's 256. You could make it 128 something. So the fact that it's a power of 2 is not super important at this point. You could say 100, 200, whatever, 50, anything you want. But it needs to be somewhat large, I guess, but not absolutely necessary. It can be pretty small. Okay, so here we are just initializing the gradient descent. We have some initial guess for our unknowns. And then we are going to do the gradient descent algorithm here. And here is where the stochastic gradient descent part comes in. Okay, so we have 60,000 images, but then what we are going to do is select using rand sample some 256 numbers from 1 to 60,000 and use just those 256 images to evaluate the function and evaluate the derivative, namely the gradient of the function in that iteration. Okay, so we're going to randomly sample 256 or how many ever images and evaluate the function and the gradient. Okay, so mini batch list is rand sample num trained data. So num trained data is 60,000, right? Then num, if you say rand sample num trained data mini batch size, copy, paste. I haven't defined mini batch size yet, but if I say 10, I'll just randomly select 10 numbers, 10 integers between 1 and 60,000. Now imagine picking 256 random numbers between 1 and 60,000, and that's what rand sample does. And then we now use X matrix, which is just those images, X matrix based on just those images, and then the output Y list just based on those images. So we are going to call this a mini batch. It's a small batch of the full data set. That's why it's called a mini batch. Okay. Using all the data, using the complete data is sometimes called the batch gradient descent. And using just a small part of the data, each step is called mini batch gradient descent. Okay. Okay, so we've got a small subset of the data randomly sampled from the whole data set. Now we can compute gradient of f, the function, but now using just this mini batch, Okay, so we are sending into the function just 256 data points as opposed to 60,000 data points. And then we find the gradient with respect to those 256 data points. And then we new iteration equals new state equals old state plus alpha times minus gradient of f, new function value, plot the function value, and keep doing that. That's it. Okay. I'm going to comment this out. This is not necessary. Um, and that's it. So we can run through this. Let me just change the mini batch size. I guess I've already changed the mini batch size to 128. Um, okay, so now hopefully if my computer is still only as fast as what it was like 5 minutes ago, I'm going to run this thing and you will hopefully notice that the gradient descent is much faster. It goes through the iterations much faster. And that's because it's evaluating only a small part of the data set each step. Of course, on the next step, it will use a completely different random sample of the full data set. So at each step, it's using a different random sample, at least in this version of stochastic gradient descent. It's using a completely different random sample of the full data set and then trying to make an improvement, a gradient step based on that random sample. And because it's evaluating the gradient and the function not over the full data set, but over a small part of the data set, which is randomly selected, we call it stochastic gradient descent because the gradient direction is not the true gradient direction, which means gradient based on the full data set, but it's gradient based on a small randomly selected data set. So the gradient direction is not quite the right gradient direction, but it's roughly in the gradient direction if you use a reasonable mini batch size. So you make progress. Okay. So, but the main point is that you'll make each iteration will be much faster because you're using only a small fraction of the data set. Okay, I'm going to run it and it's going to zoom hopefully. Okay, so notice that it's proceeding pretty fast, right? So with 50 iterations, it's gotten a pretty low value, 0.1 or something like that. Previously, progress was much slower. So notice that it sort of bounces around because it's each time it's making progress with respect to a slightly different or actually completely different small mini batch. So on one mini batch, the gradient descent says go in this direction. And on another mini batch, the gradient descent says go in this direction because it's a different sort of mini batch. Okay, so that's basically stochastic gradient descent. And you notice that because you're making progress with respect to sort of random small data sets, it sort of bounces around. It doesn't make clear, consistent progress. But nevertheless, it's pretty fast. Now it's gotten to some kind of a steady state where it's not making any more progress, and you would just stop there. Okay. I guess it's sort of still making some progress, systematic progress. So what you would want generally is sort of use the lower envelope, like the lowest point achieved in these trends overall is kind of what you want. Okay. Okay, so that's a stochastic gradient descent, and then you notice that each iteration takes much lower uh, orders of magnitude. I guess if it's 60,000 versus 128, that's an order of 6,000. No, 1,000, I suppose. 60,000 by 128. Hundred, sorry, 60,000 by 100 would be 600. So 600 times faster potentially, if not more, per iteration. And it doesn't look like the progress is dramatically slowed down because it's just using a small fraction of the image. Okay. So that's stochastic gradient descent, and we shall see even faster implementations of this in the next video.